Alrighty, so we've been talking about forces for quite a while now. Now need to move to a concept, same idea. We're still talking about net force. In 4.6 there it says, in the absence of force, objects at rest stay at rest and objects in motion continue in motion. More specifically, in the absence of a net force, objects do not change their state of motion. For example, if you push with equal and opposite forces on opposite sides of an object at rest, it will remain at rest. The forces cancel each other out, and there is no net force. The combination of all forces acting on an object is called the net force. We know that already. It's the net force that changes an object's state of motion. Figure 4.10 shows how forces combine to produce a net force. When you pull horizontally with a force of 10 newtons on an object resting on a frictionless surface, the net force acting on the object is 10 newtons. If a friend assists you and also pulls in the same direction with a force of 5, well then obviously the net force is 15. The object moves as if it were pulled with a single 15 newton force. However, if your friend pulls with a force of 5 newtons in the opposite direction, then the net force is the difference of these forces, or 5 newtons. The resulting motion of the object is the same as if it were pulled with a single 5 newton force. And that's basically just a quick summary of stuff we already know, right? Nothing too spectacular there. Okay, but now this is a bit of a new concept. Equilibrium, when the net force equals 0. So what happens when the net force is equal to 0? And the simplest answer is probably nothing. Nothing happens. Most of the time, that's a good thing. Okay? If you're building a bridge, you kind of want the forces to be net out at 0 so that nothing happens. People prefer their bridges to not fall down. People prefer their buildings to not fall down. People prefer all sorts of things to not fall down. Okay? So equilibrium is when the net force equals 0. So it says, what forces act on your book while it's motionless on a table? Don't just say it's weight. If only the force of gravity were acting on the book, it would be in free fall. The fact that the book is at rest is evidence that another force must be acting on it. This other force exactly balances the book's weight and produces a net force of 0. The other force is the support force of the table. Support force is often called normal force. As shown in figure 4.11, the table pushes up on the book with a force equal to the book's weight. When an object is at rest, with the net force on it being 0, we say the object is in a state of equilibrium. Let me find my highlighter there. My highlighter has disappeared. Equilibrium. No, that's not a highlighter. Okay. Does the table really push up in the book? Well, some individuals have brothers that claim that that's not true. Yes, just as the spring pushes up on your hand when you compress it, look at figure 4.11. You can feel the spring pushing back on your hand. Similarly, a book lying on a table compresses the atom in the table. Atoms. Behaving like microscopic springs, the atoms in contact with the book push back on it. Since the book is in equilibrium, the net force on it must be 0. The table actually pushes up on the book with the same force that the book presses down. An ant trapped between the book and the table would feel itself being squashed from both sides, the top and the bottom. Now, when you hang from a rope, the atoms in the rope are not compressed. Instead, the atoms are stretched apart. A tension force is established in the rope. A rope under tension twangs if you pluck it. How much tension is in the rope when you hang from it? If you are in equilibrium, the tension must equal your weight. The rope pulls you up and the force of gravity pulls you down. Since the equal and opposite forces cancel each other out, you hang motionless, right? And you probably, at some point in your life, probably hung from a rope, right? Now suppose you hang from a bar supported by 2 ropes. And if you haven't flipped the page over, you should do so. Suppose you hang from a bar supported by 2 ropes, as in figure 4.12. Neglecting the weight of the bar, the tension in each rope is 1/2 your weight. The total tension force acting upward, half your weight plus half your weight. Balance is your weight, which acts downward. When doing push-ups using both arms, each arm supports half of your weight. Have you ever tried doing pull-ups with just one arm? Why is it twice as difficult? Like, a lot of people can do maybe 5 or 6 or maybe even 10 chin-ups, right? Doing it one-handed is a little bit more challenging. How come? Each arm only has to balance half your weight here, right? But when you do it one-handed, you got one arm pulling yourself up. A spring scale can also be used to measure tension. When we weigh a bag of apples by suspending it on a spring, the scale reading tells us the weight. Consider a 1 kilogram bag of 10 apples weighing 10 newtons. It's really 9.8, I guess, right? When suspended by a single vertical scale, as shown on the left in figure 4.13, the scale reads 10 newtons. If instead we hang the 10 newton bag from a pair of vertical scales, as shown on the right in figure 4.13, each scale will only read 5 newtons. The two scales pull up with a combined force equaling the bag's weight, 10 newtons. Since the bag hangs at rest, the net force on it must be 0. The key concept is this: if a 10 Newton bag is in equilibrium, the resultant of the forces applied by a pair of springs must equal 10 newtons. If the spring scales are oriented vertically, this is easy. 5 newtons plus 5 newtons, right? No big surprise here, and I can actually demonstrate that, right? If I've got 10 newtons down, if it's one scale, it's got to be 10 newtons up. If I've got two scales, I've got 10, and I've got 5 and 5. So that all works fine and dandy when they're vertical, but what happens when they are not? And this is kind of important here. So let's now consider non-vertically oriented spring scales. The tension is greater in a pair of non-vertical spring scales and depends on their angle from the vertical. The angle matters. This more complicated situation is most easily understood using vectors. Recall our treatment of velocity vectors in Chapter 3. We'll now use the same vector addition techniques with forces. Force, like velocity, has a magnitude and direction and is a vector quantity. Look at the left of figure 4.14. Notice that when the spring scales hang at 60 degrees in the vertical, their readings are 10 newtons each, double the tension of the vertically hanging scales. How come? Because the sum of the two tension vectors must support the downward acting 10 Newton weight. The sum of the vectors must be 10 newtons directed vertically upward, as shown by the diagonal of the parallelogram formed between the two vectors. In other words, there has to be, if I need a total of 10 newtons, there has to be 5 newtons up vertically. And it doesn't matter about the angle. I just need 5 newtons up, and then the tension in the wire will match depending on what the angle is. For an angle of 60 degrees in the vertical or 120 degrees between the two scales, 10 newtons of tension force is required in each scale. For angles greater than 60, the scale readings would increase even more. Okay? Notice, so this is 60 newtons right here. I need, even though I've only got 10 down, right? Credit, you need to watch this. Okay? So if the scales were straight up and down, then I would need 5 and 5. But they're not straight up and down, right? They're like this. They're sideways, right? So what do I need? I actually need 10 this way and 10 this way. Why is it 10? Well, the vertical component of that 10 newtons is going to add up to 5. And the vertical component of this 10 newtons is going to add up to 5. And if I go even wider and wider and wider, I still need 5 newtons up. But because my angle is so big, I now need 20 newtons of tension. I need 5 newtons over here, but because my angle is so wide, I need 20 newtons. Let me show you. Okay? Can you spin that so that it's hanging? One more. Let's just stop. Okay, so if they're straight up and down, it should show about 5 newtons, right? Ish. But then as I go like this, what happens? What happens to the tension? Is it not a whole lot more? It's a whole lot more. Okay? The vertical component has to be 5, and whatever the angle is going to force that tension even greater, right? Is there any way for me to get this thing perfectly straight?
Pull really hard.
Hey?
Pull
it really hard? I tried that once and I almost took one in the eye. It slipped off and I caught this one. I try not to do that anymore. Notice on the right of figure 413 that the angle from vertical is increased to 75.5 degrees. At this angle, each spring must pull with 20 newtons to produce the required 10 newtons vertically upward result. As the angle between the scales increases, the tension in the scales must increase for the resultant to remain 10 newtons. In terms of parallelogram, as the scales angle from the vertical increases, the magnitude of the tension force must also increase for the diagonal to remain the same 10. Okay? What's really key is that if I've got 10 down, I'm going to need 5 and 5. Okay? And then it's trigonometry to figure out what the tension is. Okay? If you understand this, you can understand why a vertical clothesline can support your weight, but a horizontal clothesline cannot. The tension in the nearly horizontal clothesline is much greater than the tension in the vertical clothesline, and therefore it breaks, okay, because of that extreme angle. For any pair of scales, ropes, or wires supporting a load, the greater their angle from the vertical, the larger the tension force in them. The greater their angle from vertical, the larger the tension force in them. The resultant of the tension forces of the diagonal of the parallelogram they describe must be equal and opposite load being supported. As you will see when you answer the following question, the parallelogram technique of adding vectors yields some very interesting results. Okay, I'm going to get the clickers. When you step on the bathroom scale, the downward force supplied by your feet and the upward force supplied by the floor compress a calibrated spring. The compression of the spring gives you your weight. In effect, the scale measures the floor's support force. What will each scale read if you stand on two scales with your weight divided equally between them? Okay, so you've got two scales, and you are standing like that. What will each scale read? Your original weight divided by 2, your original weight times by 2, or I don't know.
We put the answer in and enter.
A, B, C, or D, yep. But what happens if you stand with more of your weight on one foot than the other? What if I lean sort of, downward on this one a little bit more? The scale you're putting more weight on will show more. The scale you're putting more weight on will show less. They will still show equal weights of your weight, or they will still show your original. In this case here, if the children are on the swings are of equal weight, which swing is more likely to break? A, which has the ropes or the chains vertical, straight up and down, or B, where they're sort of at a bit of an angle there. Which one is more likely to break? Did you just say? Consider what would happen if you suspend a 10-Newton object midway along a very tight, horizontally stretched guitar string. So I got a guitar string, it's straight across like this, right? Is it possible for the string to remain horizontal without a slight sag at the point of suspension? If I put a string and I put it perfectly horizontal, and then I hang a 10-Newton weight from it, is it possible for it to stay completely horizontal? Or would there have to be some sag? So is it possible for the string to remain horizontal? That's yes. If you think there's going to be a sag, you should answer no. All right, so what's your answer here? What should it be? B, your original weight divided by 2. It's not your original weight. Did you not see me stand up there with those two scales? Half your weight. What if you lean on one more than the other? Well, this one you got right. Hey, the scale you're putting more weight on will show more, right? You lean into it a little bit. Which one is more likely to break? I hope you said B. That's good. False. All right. Do you see your answer? The answer is no. It is not possible to remain horizontal. Not possible. Even if it's only 1 Newton, okay? Even if it's only 1 Newton. If I've got 10 Newtons down, then I have to have 10 Newtons up. And the only way to have any up is if there is an angle. There must be an angle. It might only be 0.1 degree or 0.0000001 degree, but there has to be an upward force. And the only way for there to be an upward force is there has to be an upward component, which means there has to be some angle. It just might be really small, even if it's a low E string. Or even a thicker rope. Even if it was like a big, thick rope like this, there would still be a slight little sag. You might not be able to measure it, but it would be there. Okay, now you're probably wondering what the heck is up with that. No. Right? Hunter, go get that down for me up there, please. The Romans used them, these arches like this, to send water from high areas to low areas. Okay? All kinds of different ones. You may have seen, I used to have that picture on my desktop of the arch that I saw in Greece. Same kind of thing. You could actually, what I thought was neat about it was you could actually see through the rocks. I got a little video here for you too about Roman arches. All right, so force in 2 dimensions. So we're going to talk a little bit more about this equilibrium stuff. You already know one example of force in 2 dimensions. When friction acts between two surfaces, you must take into account both the friction force that is parallel to the surface and the normal force that is perpendicular to it. So far, you've considered only motion along the surface. Now you use your skill in adding vectors to analyze 2 situations in which forces on an object are at angles other than 90 degrees. Here's 2 new words for you. Equilibrium, that you've already heard already, and the equilibrant. The equilibrant. An object is in equilibrium when the net force on it is 0. When in equilibrium, an object is motionless or moves with constant velocity. According to Newton's laws, the object will not be accelerated because there is no net force acting on it. You've already added two force vectors to find that the net force is 0. Equilibrium also occurs when the resultant of 3 or more forces equals a net force of 0. Figure 1a shows 3 forces exerted on a point object. What is the sum of A, B, and C, or what is the net force on the object? And remember that vectors can be moved if you don't change the direction of their angle or length. Okay, so what I'm going to do is I'm going to go with A and B. Whoops, that's not very good. C again. Let's draw C here. Okay, now if I add those tip to tail, there's my A, there's my B, and there's my C. What's the net force? I finished off exactly where I started, so my net force is equal to 0. So those three forces are in equilibrium. Figure 1b shows the addition of three forces A, B, and C. Note that the three vectors form a closed triangle. There is no net force, so the sum is 0 and the object is in equilibrium. Suppose two forces are exerted on an object and the sum is not 0. How could you find such a third force that when added to the other two would add up to a 0? Okay, in other words, if I only had A and B, right, let's put them over here. If I've only got A and B, what third force puts it into equilibrium? Well, we know, let me see if I can get a different color here. Let's go green. If I go from there to there, what's that force called? If I'm adding A plus B, what's that yellow one called? That one would be known as the resultant, right? If I go exactly opposite to the resultant, then my net force is 0, okay? So such a force, one that produces equilibrium, is called the equilibrant. So the equilibrant is the force that produces equilibrium. The equilibrant is the force that produces equilibrium. And it's going to always be exactly opposite of the resultant. Okay? To find the equilibrant, first find the sum of the two forces exerted on the object. This sum is the resultant force R, the single force that will produce the same effect as the two individual forces added together. The equilibrant is thus a force with a magnitude equal to the resultant, but in the opposite direction. That is the key sentence of the day. The equilibrant is thus a force with a magnitude equal to the resultant, but in the opposite direction. And if you want to do it sort of algebraically, vector E is equal to minus vector R. The equilibrant is equal to the opposite, the inverse of the resultant. Okay? And that's basically it. Here's an example. A 168 Newton sign is supported in a motionless position by two ropes that each make 22.5 degree angles with the horizontal. What is the tension in the ropes? Now, do you guys have a picture? You don't, do you?
No, sir.
Okay, well, let's draw a picture. So I have a 168 Newton sign. In other words, my weight force is 168. It's supported in a motionless position by two ropes, each making 22.5 degree angles with the horizontal. What is the tension in the ropes? So I've got ropes like this and like this, and my angle here is 22.5. That one over here should be straight up and down. I'm going to call these T1 and T2. Would you agree that the tension in the ropes would have to be, like T1 would have to be equal to T2? Does that make sense to you?
Yep.
Yeah, as long as what is also true?
Yeah.
If the angles are the same, then the tensions have to be the same, right? And you will not see any where the angles are different, maybe next year. Okay, so I'm going to call this one over here in red, I'm going to call that T1V. And I'm going to call this one T2V. And if T1 and T2 are equal to each other, then T1V must equal T2V, right? And T1V plus T2V have to equal a total of what? A numerical value. They have to equal 168. The sum of these two vertical components must equal 168. And since T1V is equal to T2V, then I could write T1V plus T1V is 168. So what is T1V equal to? (168) divided by 2, right? Because this is really just 2 T1V is equal to 168, where T1V is 168 over 2, 84 newtons. The vertical component is equal to 84 newtons. The vertical component is equal to 84 newtons. That's not what they're asking. They're asking what is the tension in the ropes. How am I going to find what T1 is equal if I know what this is 84? Well, conveniently, this is a right triangle, and I've got that 22.5, right? Need a little bit more room here. So I'm just going to redraw the triangle down here so you can see it. T1V, 22.5. This is TV. That's what I'm solving for. Opposite hypotenuse. Sine of 22.5 is my opposite, is my T1V over my T1, or sine of 22.5 is equal to 84 over T1. So of course, T1 is going to be 84 divided by the sine of 22.5. And before I go on with that, is that number going to be more than or less than 84? More than? How do you know? It's got to be longer, right? I'm looking for a calculator here. 84 divided by the sine of 22.5. 219.5. Very true. So I can squeeze that in. 219.5 newtons. Okay. One could argue that there's actually two equilibriums here, right? T1 and T2, but they are of equal value, so you could probably say that there's two equilibriums. Okay? There are a few practice problems there that you guys can try. The answers are on the back. I would suggest you start with the practice ones. I'm going to see where this takes me. I don't know if this is going to be installed or not on the computer. That's my next slide. Yeah. Okay? So try that practice problem. You know what? I'll give you 5 minutes to try that, and then I'll maybe do that one for you. Let's call it a day. Okay? Try that practice problem for tomorrow. Do it right now. Don't wait and say, oh, I'm going to do it later. Do it now.
Do we have that?
You should. Wasn't it the first one?
We don't have the picture.
Oh. Okay, you don't have the picture, right? If you didn't use all that room above, you should be okay, right? It's exactly the same question, just with 42 degrees, that's all.